My name is Nishanthi M. Subramaniam. My metric number is B08191035 and my partner name is NURUL Husna. So today I'm going to explain first question in assignment, that is, given the unit feedback system with the forward path transfer function was given on the solution. The transfer function is k over s plus 6 s squared plus 2s plus 3. So this is our transfer function, and this question have four small question on one question inside the one question. So before I go to the manually calculation, so I just try in the MATLAB for the graph. So before I got plot out my graph, so I can compare the manually and in MATLAB graph. So first I show you the command window, and this is how I insert the denominator and numerical the number, and after that this is the graph that I get. So let's go to the question 1 part A. So the part A, it's asked to find the angle and intersection of the asymptote. So the first in my calculation, I write back the transfer function was given by the question, and I find the poles and zeros. So this is my poles that I get. This is the value for the poles, and zeros we have non-zeros. So this is the calculation for my asymptote. So I get the asymptote value is negative 2.67. So I also have three angle, that is 60, 300 and 180. So I will do the graph based on the angle and the asymptote value. So second, they asked to determine the breakaway point. So in the breakaway point, we just use the equation that given above, and we do into the equation, and we just move the k before the equals, so the equation will become like this. Then k alpha equal to alpha 3 plus 8 alpha 2 plus 15 alpha plus 18. So the equation will be the negative alpha square plus 16 alpha plus 15 equal to 0. So from this equation, the answer I get is alpha equal to negative 1.21 comma negative 4.12. So actually I forget point the negative at that, later I will add on. So the breakaway point for the root locus is negative at the point negative 1.21. After that, the C is determine the axis crossing point. Okay, axis crossing point. As usual, we just take the equation from the above, and we substitute into the k. Substitute the k, and we need to find the gain. Okay, so we will do like this as a table. This all we already learned in the tutorial class, so we just follow the step that we learned before. So after we do this table, we will know the S3 what value we get, S2 what value we get, S1 what we get, and S0 what we get. So after that, we will know, we will do this part 102 minus k over 8 because from the S1. So is k is smaller than 102. Then from so we taken using the second row, S2 row with the k equal to 102. So from the equation, we just represent k as a 102 into the equation. Then we will get the answer. S2 will equal negative 120 over 8. We'll get the negative 5. So S equal to plus J 3.87. So the x-axis we get ready. So this determines that the system is stable when 0 is smaller than k and k is smaller than 102. That means 102 is bigger than k and gain is bigger than the 0. That time the system is stable. So now is our graph. this is my graph. Same. The answer is what I get is not different much. Okay, this is my asymptote, and this is my breakpoint, and this is my number of poles I get, -6 pole. My x-axis cross is 3.87, that is here. So this is the graph that I get from this transfer function. Thank you.
Assalamualaikum, I am NURUL Husna and I will continue to question number 2. Okay, question number 2 state that a system with negative unity feedback has an open loop transfer function Gs equal to k divide with s plus 1 multiply with s plus 10 and multiply with s plus 2. So figure Q1 shows the root locus of the system. For the system with the dominant poles, S equal to -1.37 plus minus J 1.4. So this is the root locus of the system. Okay, so for the question A, we need to determine the steady state error ESS of the system. So to find the ESS, the formula is 1 over 1 plus Kp. So to find Kp, we need to find K, which K is equal to 1 over Gs, which is S equal to -1.37 plus J 1.4. So we put K equal to S plus 1, S multiply with S plus 2 and multiply with S plus 10. And we substitute the S value to S negative 1.37 plus J 1.4 into this equation, and we will get K equal to 19.436. Okay, to find Kp, we need to find limit S to 0 GSHS, and we put the K value, which is 19.436, and divide it with S plus 1, S plus 2, and S plus 10, which the S value we substitute to 0. So we get the Kp equal to 0.9718. So the Kp value we put at this equation, and ESS is equal to 1 over 1 plus 0.9718. ESS is equal to 0.5072. Okay, so to question B, we need to design a controller so that its steady state error for a step response is reduced to 0 by remaining the existing damping ratio. So we need to let K1 equal to 1. Okay, to reduce the steady state error to 0, we need to design the PI controller. Okay, the general transfer function of PI controller is GCS equal to K1 plus K2 divided with S. We simplify the equation and we will get K1 multiply with S plus K2 over K1 and divide with S. So we need to let K1 equal to 1 as the question instruct us to do K1 equal to 1 and K2 equal to 0.01. I choose 0.01 to ensure it's close enough to the poles at origin. So when we put the K1 value and K2 value at this equation, we will get the transfer function for PI controller is given by GCS equal to S plus 0.01 divided with S. So the equation will be GS equal to K S plus 0.01 divided with S that multiply with S plus 1 and multiply with S plus 2 and multiply with S plus 10. So we can see that the system is type 1. So it proves that ESS is equal to 0. That's all from me. Thank you.